Hey, welcome back. Today I wanted to talk about how to find the center on a rotary table on the milling machine, or in this case of an indexing head that's mounted in line with the spindle. Hold on, you might think, well, that's super trivial and super stupid. Why in the world are you making a video that's probably taking 40 minutes about this topic? Well, there are very different approaches shown, and not all lead to a very good result. And turns out if your spindle of your milling machine if you're doing work on a rotary table and your spindle is not perfectly in line with the rotational center of the rotary table, you are creating a funny error. And the error is usually double what your offset to the center of the spindle is, of the spindle of the rotary table. It's a little bit confusing because we have two spindles in this case. We have the milling machine spindle, which is the work spindle, and we have the spindle of the indexing table, the rotary table or the indexing head or whatever your rotational work holding item is. Basically a C-axis on a 5-axis CNC mill. So how would you go to find the center normally? Or, well, normally, what's normal? How would you find the center of the rotary table? A common approach is just to chuck something up, check if it's running true, and then indicate on the item that's in the chuck to find the center of rotation. That method is flawed, because you're introducing the error from indicating the part running true to the spindle of the indexing head, and then you're centering on this already flawed item. There are ways to go around that. So let's do a little bit of indicating. First of all, you need a way to hold an indicator in the spindle of the mill. We have different options, of course. One is something like this, a small articulating indicator arm, like in this case it's made by Noga, holding a dial test indicator. Or this one. There is a set of drawings that I published years and years ago, and many people have made these. You can also buy these commercially. You can probably buy this on Alibaba for 50 cents, or you make one yourself and it's good quality. This one is unfortunately broken because I crashed it. Or you're super cool and you made one of these, my super low profile dial test indicator holder, mostly for CNC machines with very limited C height, but works also in a larger machine like this. But that has proven to work really well. Okay, let's start with the first method. Let's say we have a part like this, an aluminum ring, and we need to drill a hole pattern on this. A very common approach would be to clamp it. Then we take an indicator. In this case, I will take this low profile holder here. And first thing is to check the runout of the part. And we can use this indicator holder here right away to do this. So we bring it in. So, okay, we indicate, just rotate the part 360 degrees, and, well, it's within, let's say, I would say it's within 30 microns. This is not considering any out of roundness of the part or deflection from tri-lobing the part with a 3-jaw chuck. This is a problem. Since this is an adjustable chuck, we can cancel out the runout as good as possible. If we tighten the screw on the correct side, we can adjust the runout. Doing this like for half an hour. Okay, that's very close to 0. Now we can consider the circumference of this part, as long as we don't take it out of the chuck and reclamp it, to be reasonably in line with the center of the spindle of the indexer here. So now we can go and indicate the center of our mill spindle to the part. For that, we do a rough centering just by 4-quadrant probing, like this. Just cranking to 0 and then zeroing out the DRO, and on the second one I'm splitting the resulted value into half. Then I move to center, and then I rough centered the first axis, and now I'm repeating the same in the y-axis. And now I can do my proper indicating because I'm already within the travel of the indicator. Bring the indicator into contact with the part. Zeroing out on one side, and then we do the old spinning. So split it in half, zero out. Zero. And the problem here is already that the part is probably not round from being held in a 3-jar chuck, depending on the chucking strength. Okay, that's zeroed out. As I said, this method is flawed. It's not perfect. We will see what the difference to the real center of rotation later is. There's a method to find the real center of rotation without transferring the center of the... What we basically did is we took the center of the spindle and transferred its location to the part held to the spindle. And then we transferred this measurement again to the position of the mill spindle to the part. So that's why I'm saying it's flawed, especially if the part is not round. Let's say this part is held very strongly in this chuck. And let's crunk down on this a little bit more, like normal chuck pressure. Now we get an extremely funky reading all around. And suddenly indicating gets very, very hard because the part is not round anymore. Now it's tri-lobed. Let's try this again on a second coordinate system. So let's look at the 4 quadrants. Over here we still have 0. Here we are minus 30, 0, and plus 20 microns, that is. So we're already in a pickle situation here. So let's try to center this again. So 0, 0, and in the X orientation, we can kind of center it, but we get extremely wonky readings between the jaws. So this is not really good. Well, it's not good to push a part out of round, but just for the sake of demonstration, this is what I'm doing here. So how the heck would you find the center on this part now? Well, you could cancel out the error just by rotating the part along with the indicator. I'm not sure if this technique has a real name. I have seen this done on real jig borers to center rotary tables, and I'm stealing this method for my purposes on a tool room mill, and I'm calling this method single point indicating. you mark a spot on your thing that you want to indicate. And you look at your indicator reading. In this case, it's already 0. Then you spin the part 180 degrees and you line up the indicator with your felt marker marking here. Then you center it again. You do your dance back and forth until you get 0 or the same reading on both sides. Like this. And we do the same in the y-axis, always lining up the red mark with the indicator. And we adjust to 0 and we check in the other orientation. And we get 0 here too. We zero out the DRO in this position. Okay, let's say you don't want to indicate on a questionable round part, or you have nothing round on your current setup that's round and seemingly in the center of the spindle. How about that? Well, let's use a technique that I would like to call single point indexing or single point centering. You need to stick something to your rotating axis that you can indicate and create a single high spot. For example, a tooling ball on a magnet, or in my case, it's a pin on a magnet. Somebody made this at my old day job. It's a magnet, surface ground parallel, and a piece of steel, surface ground flat on both sides, and a pin in the center. Nothing on this needs to be surface ground, to be honest. But it's nice. So it's just a pin on a magnet. And we just stick it somewhere on our rotating axis where it can reach it and where our indicator can reach it. And I move both the axis of the mill into oblivion compared to our last setup, so we start fresh over. I zeroed out the DRO here in the void. And I like to do this I like to start in the x-axis. For that, I adjust my indicator to be at 3 o'clock. Then I rotate the spindle of my indexer also roughly, so the pin and the center of rotation of the indexer form a line that's kind of in line with the x-axis of the machine, and the pin is also at 3 o'clock. Then I use the x and y motion of the mill to find this pin, and I just find the high spot and I move it to a convenient number like 0. And in this position I zero out the x-axis of the mill. Now I spin over to 9 o'clock and I rotate my pin also over to 9 o'clock. It's of course far away because my travel of the my radius of the indicator does not match the fly radius of this pin. And I just crank in until I hit 0, find my high spot, go to 0, and now my x-axis shows a random arbitrary number that's just set by where I put the pin on my rotating axis and to what radius the indicator is set. We take this number and we split it in half. And then we crank the x-axis to 0. Now we do the same in the y-axis. We go to 12 o'clock. We move in till we hit the pin with dial test indicator. We find the high spot and we crank to 0. We zero out the y-axis. Go to 6 o'clock. Rotate the pin also to 6 o'clock. At this point it's basically always the same that we're doing. Find contact, find the high spot, go to 0, and we look at the DRO, and we get an arbitrary number, 15.175. It's different to the upper number because this is all not very precise at the moment. We take this number, split it in half, and we crank to 0. roughly. Now we go to 3 o'clock so you can see what's going on. I crank the pin here also to 3 o'clock. Now we're roughly centered on the center of the indexer. Now we bring our indicator into contact with our pin, just like this. And we find our high spot, and this high spot we zero out the dial test indicator. Go to 6 o'clock, 9 o'clock, sorry. I have a digital watch, I'm really bad at clock faces. And we get a reading. By finding the high spot we get 17. 17 divided by 2, that's 8.5. So we crank the x-axis until the indicator shows 8.5. And in this position we zero out the dial test indicator again. Double checking our zero. Okay. And now we can do the same in the y-axis. That's then already fairly precise. And I like to do the fine adjust with the rotation of the indexer then. Okay, this is our high spot, and I'm moving the y-axis to 0. I'm moving the y-axis to 0 out the dial test indicator. Now we repeat this at 6 o'clock. Okay, and we get a reading of plus 20 and a little bit. Plus 20 and a little bit. So we split this in half by moving the y-axis just a tiny bit. And we zero out the dial test indicator. Okay, we're 0. And now we can do the same again in the x-axis. And by doing this twice, you are pretty much there. So 9 o'clock. 10 micron too low. This is sure. Okay, 0. Now we go to 3 o'clock. Check again. And that's 0. Now we go to 12 o'clock. And that's 0. Check again at 6 o'clock. Filming this is, by the way, super annoying because I have to move the camera constantly so you can kind of see what's going on. So that's 0, 2. So now, and also it should be 0 in all in between positions too, so we can just for fun do it here. And that's 0. You can kind of march your way around like this. Because there is no roundness error of any calibration artifact that you're putting on the table. You're using just the spindle and the error motion of the spindle to indicate. Speaking of error motion, I hope you have watched Silo's Garage videos on spindle metrology. If not, run out and do so. I will put a link in the description. He knows a lot more about spindles and indicating than I do. 0 over here. And 0 over here. So can be very, very confident that this is the true center of my indexer spindle. Now that we found the true center of rotation of the indexer, zeroed out the DRO in this position, let's go back. This one, that's by indicating on the rotating aluminum part. I spun or I indexed the part along with the indicator to cancel out any error of the out of round part. That's within 6 and 2 micron. Is 6 and 2 microns much? Nah, not really. This is a manual tool-room mill. It's not a jig borer by far. For most applications, this is very good. Let's go back one more. -4 and -8. This one was indicating on the stationary aluminum part that we adjusted to run true with the indexer. And then we indicated on the stationary item. So -4 and -8. It's already a little bit more. Now let's go back furthermore. 0 and 0.02, 2 micron. This I did beginning of the day today by single point indexing on the magnetic pin. So that's very repeatable. And one more. This one I did yesterday. 7 micron and 2 micron, also by single point indexing on the magnetic pin. I can explain the deviation between those two by temperature drift. It's winter and the temperature in the shop during the night drops by 7 or 8 degrees. Closer, I'm pretty far from the heater here on the milling machine, probably even a little bit more. So this can very well be thermal drift of the entire machine. But this was earlier today and this was 5 minutes ago. So that's very close. That tells me that this method is extremely repeatable. And this method does not need anything round on your index, on your rotational axis to indicate. This gives you the true center. At first I wanted to do a super fancy demonstration with cutout paper models and drawings, but starting to do this demonstration here in person, I figured it's good enough to be shown this way. It's I think it's a very practical way of doing it and finding a very precise center. And by the way, why is the center of rotation so important for when doing rotary table work? It comes especially into play when you're drilling something like a hole pattern on a pitch circle. Oops. When you're drilling like on a 60 millimeter pitch circle diameter, a number of holes, and those hole locations need to be very precise. That's why we drill on a milling machine or go to a jig borer. This technique, by the way, translates very well to other machine types too that have some kind of an indexing feature on the table. Let's say you want to draw a hole pattern. When you're off the center of your rotation by, let's say, 50 micron, then you move out to your radius of your hole pattern, then you rotate the work 180 degrees, you get double the error. Then suddenly your 60 millimeter pitch circle is 60.1 millimeter. So things you get very, very easy into trouble when drilling hole patterns on a rotary table, or an indexing head for that matter, when your center of your rotation with the mill spindle is not perfectly on center with the indexer. Get really into trouble. And I have gotten into trouble for that on parts. At first I couldn't figure out why, until I sat down and sketched it out and thought about what's going on. Oh yeah, and I know that coaxial indicators exist. I don't like them. Can't care less about them. I think they are a solution to a problem that nobody asked for. They're just introducing an additional error source. Dial test indicator is a nice thing to have. Moore had a pretty cool setup with a wireless electronic indicator, but those are rare. But a 10 micron or a 2 micron dial test indicator is pretty darn good. Oh, in case you're wondering about this tool holder in the spindle. So, in case you're wondering about this tool holder in the spindle of the mill, this is an adapter from 40 taper to HSK 32, because I have a pile of HSK 32 tooling for the CNC mill. I thought it would be nice to have the option to use these tools, and especially, for example, the indicator holder here, also in this machine. I purchased an adapter from Göring. This is what they look. They have a 40 taper and they have an HSK interface. So this is what they look. They have a 40 taper. I added the special Deckel S20x2 pull stud in the back myself. These are off-the-shelf items. And they have the HSK interface in front here. And the way this works is you have your face contact for the tool holder, because HSK makes contact on the face, back on the flange here, and on the taper. The taper is of course on the inside here. Then you have this gripper assembly here, which is kind of free floating, and this expands into this recessed pocket in the hollow shank taper. That's what HSK means. Hohlschaftkegel, hollow shank taper. The gripper grabs the tool inside this recess and pulls it back into the taper. The taper makes contact and the face does not make contact. It gets pulled in further and further. The taper collapses a little bit. Then you have dual contact on the taper and on the face. Just like with a lathe short taper spindle, like a cam lock spindle. And the way this gripper here works, you have a Allen key, you go in from the side, you just tighten it, then it widens. So it's super neat. And the HSK tooling has of course a hole here, so you can poke with the key through the hole into the gripper assembly. Super simple. So this goes in here and you tighten it. Normally you use a torque wrench. Torque wrench is over at the CNC. And you tighten it a little bit. You close this little brass ring here. It's spring loaded. This is just so no chips can get into the mechanism in there. And then you have a HSK 240 taper adapter. And to change the tooling, you just open this brass ring. You open it all the way, you back it off a tiny bit. It's a super fast and super repeatable tool changing. That's the same manual HSK system as on my CNC milling spindle. And really, really happy with it. Would buy it again. And this is made by Göring and it's very, very expensive. I think list price is 400 euros. So you better have a good reason to buy it. I think it would be unfair to leave a horizontal spindle indexer out of the equation, or vertical spindle and horizontal spindle mill. So a 90-degree arrangement between the machine spindle and our indexing spindle. So I dug out my old Vertex rotary table. Longtime viewers might remember this guy that I rebuilt in 2017. That's 7 years ago. And I still use it to this day from time to time if I just need a rotary table. Despite most of the work being done by the indexer of the Deckel mill nowadays. But it's still going strong. So how do you find the center of this rotary table in the y-axis? So back and forth. You could indicate on the platter if you're certain that it's running true, but that's dangerous, as usual, because you kind of don't know really how round it is and how well it runs true. You can check how true it runs, but it's kind of annoying to indicate. But again, our friendly little magnet helper comes in handy. We can stick it to the face, and now we have something to indicate on. And in this case, it's a little bit more annoying than with the vertical indexer, but still very, very doable. Okay, I rearranged the entire indicator setup so the indicator face is horizontal. And what I'm doing is I'm just moving the pin at roughly the same height as my indicator probe tip. This does not have to be on center line with the indicator, which is great with this technique. You will see in a second why. So kind of bring it on center height, and then I bring the indicator into contact with the pin just by moving the y-axis of the machine. Bring it in contact, give it a little bit of preload, then I rotate the spindle by hand to find the high spot. That's kind of here. And with the high spot of the indicator, I'm also running rotating the pin I decided to go to the outside of the pin because that's more favorable with the indicator reading. I'm just going to do this, this, and this. This is easier to read for me, or it's easier to not over travel the indicator. So going to sweep again by rotating to a low spot, and then I'm doing the same with the rotary table, sweeping it to 0. And in this position, I'm zeroing out the dial test indicator, double checking, doing the same with the rotary again, and I zero out the y-axis on the DRO. Okay, fine. And now I rotate this thing by 180 degrees, make sure I don't crash into the face of the rotary table. So I'm cranking it clear a little bit. And I'm moving the pin over by rotating. How far? The indicator will tell me. I don't know how far I need to go. Does not really matter. So, bringing my y-axis in, bringing my pin close to the probe, finding my high spot with the rotary table, find my high spot with the spindle by sweeping. Okay, this is the high spot. Move into 0. Double check. Looking at the DRO, we have a random number in the y-axis. We take that number, split it in half. Crank the y-axis to 0. And this should be y-axis 0 now, or this should be center of the rotary table by now. We can double check that, of course. We don't touch the y-axis of the machine now. We just adjust our dial test indicator to make contact with the pin. It doesn't matter where. We can just go to here, because I feel like it. So we sweep, move the x-axis in a little bit. We sweep like this, and we sweep with the pin. Let's go to the outside of the pin. That's better, because we can't over travel that way. Okay, we zero out the dial test indicator in this position after we found the high spot with both the rotary table and with the mill spindle. Okay, we give it a little bit of tap to see if it's really zeroed out. Sometimes that's not the worst idea to do. And now we sweep over. When you sweep off the end of a pin like I did, be careful to not over travel the indicator. That's very easy to do. Now just crank over until we hit the probe of dial test indicator again. Just like this. We find our high spot and we sweep. And we are within, that's not 0. That's more like 15 micron. So we have 15 here, and I want to split that in half again. So kind of to here. Keep in mind, what I'm reading here is double the error that I get in reality to be off center, because we're doubling the error by flipping it 180. So we're 0 here. We swing over again. And we come back with our pin. With a little bit of practice, this gets very quick. We find our high spot with the pin and with the spindle. Yeah, that's like 7 microns plus. I call that good enough for y-axis centering. That's in many cases not as critical as on when you're working on the face of a rotary axis. Okay, that's fine and dandy. That's the center of. Now we found the center of the indexer. But how do we know I'm not pulling a leg on you? Because, Stefan, you are not indexing 180 degrees. You're not using a tooling ball. You're just randomly cranking around with the rotary table and the spindle, finding high spots, and well, it works. It really works. Let's do an idiot check. Let's compare it. Let's say you have the option, because this is an indexer with a Morse taper in the center. You can put in a test bar, or in this case a mill arbor. This doesn't run terribly true, but it's okay usually. Let's sweep this. We're basically using the same technique here. Getting into contact, finding the low spot, zeroing out the y-axis. Swinging over 180 degrees. Hope we don't run out of y-axis travel. Get into contact, sweep for the low spot. And we take the number in the DRO, split it in half, crank to 0. Bring the dial test indicator into contact again, so we can do a sweep without a y-axis movement. So we have our high spot here. Again, so you can see something. Sweeping back here on the mill arbor. Let's move it. It's not perfectly 0. And sweep to the front here. Let's adjust a little bit. And this is 0. This is good enough. So, and let's compare these results. I zeroed out on the result with the mill arbor 0, 0, 0. Coordinate system 4, this was indexing with the pin on a random position on the rotary axis. And earlier today I did the same already. Well, before I did the demo in the video, I did it off camera and I have -10. Which result will I trust more? Probably these two, because these do not take runout error in the Morse taper socket and the runout error in the mill arbor that I used to indicate the center into account. So yeah, the difference between those three results is not very much, 10 micron at most in this case. But 10 micron off center is already 20 micron error if you mill, for example, two parallel surfaces with the part swung 180 degrees. So that's a thing to be considered. Sometimes you have to cut high precision features by indexing 180 degrees, and then this becomes a problem. And really, I have to say, if I could give one tip to beginners with milling machines, learn to be good with dial test indicator. Learn to use it for everything. In the beginning, it's atrociously slow and you will curse quite a bit, but the confidence that you get from an actual reading of a dial test indicator is so much better than most other means of adjusting position of a mill spindle in relation to your work. No matter if you're picking up bores, finding edges of work pieces, or center out rotating axes. It's a super powerful tool. It's cheaper. A Heimer probe is of course super user-friendly. But in reality, you have to double check them very often. You have to use it 180 degree opposed, and then it's convenient. Let's say it that way. I don't want to hurt people's feeling that like them. I don't like them at all, not the least. I think nobody should buy them, but that's just me. So if I could give only one recommendation to beginning machinists who learn how to run a manual mill, especially hobbyists who do not have high-end machines with 3D probing in the machine, in a CNC machine, learn to be good with dial test indicator. Use it for everything. Don't take shortcuts with other means, with wigglers or something like that. A dial test indicator gives you an actual reading and it shows you what's going on with your setup. And since it's spinning with the spindle, it's a single point thing, it's not relating to the runout of the spindle. A HIMA probe, a HIMA 3D Taste, needs to run true. You need to indicate it in, you have to adjust it to run true, then you can use it. I don't like them. That's my disclaimer. I purchased a new one because I wanted to see if I like them today, not like 10 years ago, but nothing has changed. I still don't like them. I sold it again. I think they are a gimmick. They are very fast. They are great for if you're probing raw stock, but I don't think they're a great tool for high precision work. The dial test indicator, on the other hand, that's a great tool for precision work. You can use either a 10 micron, like I do most of the time, or you can use a 2 micron dial test indicator if you want to make yourself crazy. Keep in mind, these are milling machines, not jig borers. They are not perfect machines. If you're running a Moore number 3 jig borer or jig grinder, things start to look different. Those are some of the best machine frames that had been made, or Hauser jig grinders, or if you have a Deckel LKB jig borer frame. Those machines, those are more like a measuring machine that accidentally have a machining spindle bolted on. Also, they are just inherently more precisely built machines. But we can do a lot with a standard milling machine, and there are techniques that help us to get the most of it. Like this. This is a great way to find the center of an A-axis if you have nothing really good to indicate on it. Also, I would say I see often an obsession with test bars. Don't buy a test bar. A test bar is great if you do machine rebuilding, but I don't think you need a test bar for general, if you're a machinist. Kind of a waste of money, I would say. So that's the horizontal spindle indexer, or A-axis. So I hope you enjoyed this little tool room tip. I hope I was able to explain the concept of single point indicating reasonably well, and also make it appear to be a practical approach compared to taking something, make it run true, and then indicate on this item. The intermediary step is something that creates error and also takes time. So the single point indexing or single point indicating seems to be slower at first, but when you consider everything in, it's very viable. And also it's dead accurate because you have only the error motion of your spindle creating problems, additional problems. You also have the problem of your dial test indicator not being perfect and your milling machine spindle not being perfect, and suddenly you're facing existential dread in your shop. So I hope you enjoyed. Thank you all for watching. Thanks for the support, and I'll be back.